we've already talked about different types of constitutional isomers. So constitutional isomers, just to make sure everybody remembers, is when you have the same molecular formula, but the connections of the atoms are different. So for example, instead of having maybe a pentane, you could have 4 carbons in a row with another methyl group there. Those would be constitutional isomers. Now we're going to start talking about what's known as stereoisomers. So this is when you've got the same order of connectivity, but in 3D space, the arrangement of atoms is different. Okay, so that's what's really going to make a difference here. Now, I would implore you to please get out a model kit and look at these for yourself. I tried to make a video with one. It did not work for some reason. So we're just going to have to do this in note form, okay? Remember, last chapter we already saw a little bit of this stuff. So in the Hayworth projections, we saw where we could have chlorines on the both sides, and we refer to that as a cis arrangement, versus if we had those on opposite sides of the cyclohexane, we would refer to that as trans. Well, that's basically what we're going to apply as well when it comes to double bonds. Now, please know that this is only the case with double bonds. Again, take your model kit out and prove that to yourself. Because when you have a double bond, what you also have there is you have sp2 carbons that are involved in that here and here. So remember, what that means is that there are 2 more things here, and those are presumably hydrogen if they're not written in otherwise. Well, that double bond gives some rigidity to that bond. It cannot rotate. Like, unlike when it comes to a single bonds can rotate and spin, but this double bond cannot rotate because it's locked into position. And that's the reason why when it comes to double bonds, we can also designate cis and trans configurations. So what that's saying is that this CH3 and this CH3 are on opposite sides of that double bond, and that's why we would call this trans, okay? So what you have here is you have the 2 carbons involved in the double bond. One of them has a carbon going in one direction, the other one has a carbon going in the other direction, or a substituent going in the other direction, and that's what makes that trans. On the other hand, if you have a double bond with a cis configuration, what that means is that we have one of the carbons involved in the double bond with an R group coming, or a substituent coming in one direction, and then the carbon in the double bond is also the other one. So the one right here, right? That one has a substituent also going in the same direction as this first substituent here. So they're both going in the same direction, whether that be up or down, and that would be the cis to pentene. So just to mention this, we're going to get to it later, but instead of being an alkane, these are alkenes, and they end in ene because they have a double bond in them, okay? So let's go back and start looking at what else this term stereoisomer can mean. So let me give you some basic information here first. So we can call things a stereoisomer, or another word that's often used is the term chiral. Well, chiral can be a chiral center, or you can have a chiral compound. Chiral compounds are those that have non-identical mirror images. So if you think about like a mirror image, let's say if we have a mirror image of something that's really simple, like a sock, right? Like the mirror image of that would kind of look like that. Now, granted, it's my drawing, so it's not great. And so if I rotate these, they could sort of like be the same if they actually were drawn properly. Well, so in this case, that is not a chiral type of shape. It's just not, because those 2 things, when you have the mirror image, they will be the same. So I would also say that when you have an sp2 carbon, the mirror image will be the same. Okay, so you don't have to worry about times when you have sp2 carbons. But if we have another set of parameters that occur, let's just go with that for now, then the mirror images are non-superimposable. And that's to mean that when the mirror images occur and they're not identical, when you put them on top of each other, they're not going to be the same. Okay. So going back to that, this is going to happen when carbon has 4 unique groups attached to it or atoms attached to it. So what this means, y'all, is that you have to have an sp3 carbon. So chiral atoms are going to come in 2 forms. We can have them as kind of a left hand versus a right hand. So like if you were to put your hands on top of each other and try to say that they were superimposable, your thumbs would stick out, right? And so the same way that you have a right hand and a left hand, so do molecules. Each of those are separate stereoisomers. That's the case if you only have them differ at the stereo center, which is the chiral atom, yep. Okay, so here's what I mean by that, okay? So if we have a molecule like you see here to the left, we've got a blue ball sticking up, we've got a purple ball sticking out to the left, down and to the left, and then we have red and green. Well, if we put the mirror image there on the right-hand side, you can see that. So what I've done here is I've then taken the molecule to the right and rotated it, right? So what that will do is it basically takes this purple one and it brings it over here, right? That would put this way, and this goes this way. So that means that green now is in front and red is here in the back. So see how I can compare that with what we started with. And they are not the same. The blue and the purple are in the same position, but the red and green are backwards. And this will happen if you make that model kit. 2 of them will match, the other 2 will be backwards. You can keep trying to do it, you will see that 2 of them will match, the other 2 are not the same. And that's because of this chiral center. We've got a stereo center at the sp3 carbon right here. And so those are 2 different molecules. So you might want to know how in the world we spot these things. Well, generally speaking, if I see 3 things that are attached to a carbon, a little flag goes off in my head and I go, I should at least check that out. Because remember, if we're looking at that carbon right there, what's not drawn in is the fact that you've got a hydrogen coming off to the back. So yes, there's actually 4 unique things there. Now, one thing that you might be saying is, but look, this carbon right here, there's a carbon attached to both sides. And those are the same. Well, there's a carbon attached to both sides, but they're not the same. This carbon on this side is a CH3. This on this side is a CH2 followed by a CH3. So remember how I said you have to have 4 unique atoms or groups? Well, that means you can consider this is one group and this is another group. And that can go far down the line before you actually have a change. And those 2 configurations will be different. Okay? So another example of that. This first example here, remember we've got another hydrogen here in the back, so that's still there. Now in this case, when I go this direction and I go this direction, they're the same. So this is not a chiral molecule. However, in this case, this direction, I hit another CH3 pretty quickly. This direction, I don't. And considering the fact that we've got a hydrogen right there, this one is chiral. And we have a stereocenter right there, okay? So if you have three different things coming off of a point, whatever that may be, and you can circle it and either come up with a peace sign or a Mercedes sign or whatever you want to think of that as, then that's something to at least check out. Okay. We've talked already, though, about things that kind of looked like that. So what does it mean when you just have a straight line on those? Well, what that means, generally speaking, is that we have not designated that you have a specific handedness to that particular substituent yet. So we haven't said that you have that methyl group or either of those methyl groups coming towards you, away from you. So what we're assuming is that we're dealing with a mixture here of different types of things. So if it's not specified, it's not that that's not a chiral center. It is a chiral center, but the specific stereochemistry has not been identified in this case. Okay, so that's something to look for. Another type of writing that we use a lot of times, specifically in biochemistry, is something called a Fischer projection. So that's Fischer projection. These kind of go hand in hand with that Haworth projection. I'm just exposing you to this at this point. Nothing really intense with this. But it's really kind of weird when you look at this flat. And I wish that I had a model kit to show you right now, or wish I could show you that without the entire video going a little bit wonky. But what's happening here is that we have a carbon. And as we move back, like each of these crosshairs is also a carbon. And the carbon that comes next kind of keeps looping backwards. So by the time you get 5 or 6 of these, you practically have made a ring, even though it's not really attached at that point. So if that keeps moving backwards, what that's telling you is the stuff that's coming this way and this way is actually pointed towards you. So again, I would please make a model kit. This feels really strange. It's not necessarily putting things in zigzag formation like what we're used to. But that's how we make it, and that's how we draw it. But each of these, when you have 4 things that have come together, you want to check that in this type of formation for a stereocenter. Next, we need to figure out how to name these things because 2 different arrangements of atoms need to be named separately. By the way, if 2 things have the same name, that means they're the same. That's kind of how that works, okay? So let's talk about this. We're going to use what's known as the Kohn-Ingold-Prelog system. And basically what we need to do is we need to start by assigning each substituent around the carbon atom a priority. So priority goes to the largest atoms first. The largest atom takes the first priority or the highest priority. And it's weird when I say highest, it's really the lowest number. So, takes the number 1 position. From there, you just keep applying subsequent numbers by atomic number. Now that's if everything's sort of different. But what happens when we have groups that are not identical that we need to assign from there? Well, first we deal with the biggest atoms first. So those are what's going to take priority first. And then we basically get to the one that gets the biggest fastest gets the highest priority or the lowest number, okay? Okay, so here's what I mean by that. So here's some examples that we've got. This is the stereocenter right here. Keep in mind, just like we saw before, there is a hydrogen in the back. And that hydrogen in the back, he's tiny. He's going to get a number 4. He's going to be left out. Well, chlorine is the biggest atom. So chlorine takes number 1. Then what we're going to do is compare this carbon to this carbon. And usually I leave hydrogen out of this because they're pretty small, and that's not what we're really comparing at that point. But in this case, we've got a carbon right here that's attached to another carbon. And in this case, we have a carbon that's not attached to another carbon, which means that this group gets bigger first. That's the reason why it gets the lowest number between these two, okay? So that's how we do that type of assignment. Over here, we've got chlorine, fluorine, and then we have 2 carbon groups. So just like we sort of did before, chlorine's the biggest, he gets number 1. Fluorine's the second biggest, he gets number 2. Then we start going down the line. This carbon, they're the same. So we go to the next thing down the line. This carbon has 1 other carbon. This carbon has 2 carbons that it's attached to. Therefore, this gets the lower number or higher priority. Thinking about this, let me make sure that we're clear on this. Let's say that you were to have something like this, and this was to happen. Chlorine's going to get number 1 priority, right? But then we have different ways that we can travel from here. We can go that way, and we can go this way. And you may say, oh, well, this is a bigger group. And look, I can keep adding stuff. It's not going to change anything. Here, let me go back and add that, just to make sure that you all get this concept. Because here's the thing. Here we have a carbon, and it's attached to 2 carbons. Here we have a carbon that's attached to 1. So that's what I mean by the gets the biggest fastest. This is not as big, it doesn't have as many carbons, but because that first carbon, you get more things attached to it, that's going to take second priority. This carbon is attached to only 1 other thing, it's going to take the third priority. Okay, that can be a little bit confusing at first, so I hope that you followed along. If you didn't, go back and review that. Okay. Now we have one other set here. So we're going to have a methyl group in each of these, and we need to identify also where the hydrogen is. So remember here, we've got hydrogen in the back because the methyl group's coming towards us. And so in this case, we are prioritizing 3 carbons. If I go from here, this gives me carbon, carbon, carbon. This one is done at that point. He's going to take the lowest number. But then we keep going over. This carbon is attached to 2. This carbon's only attached to 1. And that's the reason why this is a number 1 priority. Okay, that takes number 2 priority. The same concepts hold true from the other side. Okay, let's go back and do the other one. And I will change colors. So in this case, the H is coming towards you, right? That would be where that hydrogen is. That's going to take number 4. And then we have to consider what gets 1, 2, and 3. Just like what we did up above, 1 is going to go to the side of the ring that is going to get to the most carbons first. 2 is going to go to the other side, and 3 is going to go just to the CH3. Okay? So to continue through this process of how to identify these names, what we tend to do is place the group with the 4th priority towards the back. This is the easiest thing to do. However, there are ways to get around it. And so I'm going to show you that in just a minute, okay? Because there's times that you need to have alternatives. So let's say that you do have the 4th priority towards the back. Then from there, what do? Well, we are going to figure out if we have an R versus an S configuration based on which direction, if that was a wheel, the wheel would be turning. If you connect 1 to 2 to 3 and 3 goes back to 1, and that turns to the right, we refer to that as the R configuration. If we connect 1 to 2 to 3 and it goes to the left, we refer to that as the S configuration. So, in this case, 1 goes to 2, 2 goes to 3, 3, we skip 4 and go straight back to 1. That is going to the left. That would be the S configuration. On the other hand, if we go to the other one that we just did here, well, the first problem is that we have the CL in the back. It's the top priority. So we have to rotate this in a way so that the fourth priority can be in the back. This takes practice. The other thing that you could almost do is almost do what you would do for a Newman projection and kind of look down this way with your eye, like if you're coming in this way and looking that way, but you're really just looking at this one carbon, not necessarily both of them together. But if I'm looking at it from that direction, then the fourth would be in the back. Or you can rotate this so that the fourth is in the back this way. Either way that works for you, that is totally fine. Or maybe you want to use the method that I get to on the next page. Any of those work. But in this case, since I've got this rotated out, I'm going to point out that we go 1 to 2, 2 to 3, and then 3 circles back to 1, and that is the R configuration. Okay. So now all we do is we add the designation to the beginning of the name in parentheses. And if you need to put the numbers with these because you've got more than one, we'll get to that as well. So this becomes S2-chloroheptane. And this would become R, 3-chloro, 3-fluoro, 2-methylpentane. Okay, so that's just the new part right there. And I think I forgot an L in there somewhere. Okay. Well, what happens when we have things like that ring where sometimes you have the priority in the back and sometimes you got it in the front and you can't really start rotating a ring all over the place? Well, it's easy to also look at things if instead your top priorities or your lowest priority is directly aiming at you. So it's right in front of you. So if you instead leave the lowest priority facing you, then basically you just take the reverse rotation when you're done. So for example, if you were to take this piece of paper or the screen that you're looking at right now, and I'm rotating to the right, if you're on the other side of the screen and you see somebody rotate to this way, they're rotating exactly opposite to what we see on this side of the screen. So if you do what you're supposed to do, but your lowest priority is coming at you, then just reverse it. So the first way, in this case, hydrogen's in the back, we continue to do what we did before. So 1 goes to 2, 2 goes to 3, 3 goes back to 1. This is an R. So we're good. We still got an R there. But on this bottom portion, we've got a hydrogen facing towards you, right? Well, okay, so let's figure things out. If we put 1 goes to 2, 2 goes to 3, 3 goes back to 1, that is going to the left, but the lowest priority is in front. So we just need to reverse that. And what that means is that both of those are R. Now, I messed up the notes here, so please do correct it. This should say 1,3-dimethyl. So that should be in there, okay? My apologies. So the name should read 1R, 3R. See how that's in parentheses? And then we say 1,3-dimethylcyclohexane. And with that, you all have learned how to name and designate R from S. Good job.